Deep within the processing core of a NOAA supercomputer, a single value is quietly ascending. It is a number that, for the moment, remains largely unmentioned in wider public discourse, yet its implications are profound. The last time this figure rose so high, and with such speed, a weather phenomenon was linked to a global catastrophe that resulted in the loss of an estimated 30 to 50 million lives, a death toll exceeding the military casualties of the entire First World War. What makes this historical event so chillingly relevant is that the scientists who analyzed it did not attribute the disaster to the weather alone. They identified a very specific, three-part oceanic configuration as a key driver. As of this week, all three of those components are once again moving into alignment. The pattern assembling in the data has a name, and its re-emergence warrants our full attention. This story will evolve as new information arrives in the coming months, and we invite you to follow Calm Space as we continue to monitor its development. To understand the forecast, we must first look at the present. At this moment, the vast Pacific Ocean appears to be in a state of profound calm. This is not a metaphorical observation, but a literal, measurable, and statistical fact. If you were to examine the oceanic Niño index today, the value in the most recent column would read approximately plus 0.16 degrees Celsius. This figure is so close to zero that the vast majority of climate scientists would simply describe the conditions as neutral. The ocean is not unusually warm, nor is it unusually cold. It is simply existing in a state of near-perfect equilibrium. For any forecasting desk, such a number would typically signal that there is nothing of immediate or urgent concern to report. It represents a baseline, a quiet interlude in the planet's vast climatic rhythms. And yet, here lies a profound and unsettling discrepancy. The world's most advanced climate models are forecasting a future that starkly contradicts this present tranquility. This isn't the prediction of a single rogue model running an experimental simulation. We are referring to the two most respected, institutionally trusted, and independently developed climate forecast systems on Earth: NOAA's Climate Forecast System version 2, or CFSV2, and the North American Multi-Model Ensemble, known as the NME. In the late spring of 2026, both of these systems are converging on an identical forecast. They are pointing toward a number that, the last time it manifested in the real world, was associated with the deadliest pandemic in modern history. That number is an anomaly of plus 2 degrees Celsius or higher in the Niño 3.4 index. The models are not treating this as a remote possibility or a statistical outlier. They are approaching this forecast with a quiet but firm consensus that causes seasoned analysts to pause and pay very close attention. To appreciate the gravity of this forecast, it is essential to understand the instrument used to measure it: the Niño 3.4 index. This index serves as the standard scientific yardstick for defining El Niño events. It measures the sea surface temperature anomaly, that is, the departure from the long-term average in a specific rectangular region of the central Pacific Ocean. This area is located roughly between 5 degrees north and 5 degrees south latitude, and from 170 degrees west to 120 degrees west longitude. When the temperature in this region climbs more than plus 0.5 degrees Celsius above average for 5 consecutive overlapping 3-month periods, an El Niño is officially declared. A reading above plus 1.5 degrees signifies a strong El Niño, but crossing the threshold of plus 2 degrees places us in a different category entirely: a super El Niño, an event so rare it has only been confirmed 3 times in the modern instrumental record: 1982-83, 1997-98, and 2015-16. The current models are not merely suggesting a modest or even a strong El Niño. The core projection from the CFSV2 ensemble, the collection of individual simulations the model runs, is settling between plus 2.1 and plus 2.2 degrees Celsius at its peak. Some of these individual simulations are running even hotter, projecting anomalies as high as plus 2.5 to plus 3 degrees. This alone would be a remarkable forecast. But what elevates this from a point of interest to a matter of serious concern is the independent verification. The NMME, an entirely separate modeling system built on different physics, different assumptions, and different starting data, is independently converging on the very same temperature range. This convergence is not a minor detail. It is the central, most compelling element of this unfolding narrative. It raises the critical question of what it means when two independent witnesses begin describing the exact same improbable event. It is crucial to remember that climate forecasting systems are not infallible oracles. They are intricate numerical representations of our planet, built from complex equations that describe the flow of heat, moisture, and momentum between the ocean and the atmosphere. By their very nature, they contain known biases and are prone to error, especially when forecasting far into the future. Small uncertainties in the initial conditions can grow exponentially over time. Consequently, the normal state of affairs in ENSO, forecasting the El Niño Southern Oscillation being the larger climate pattern, is one of spread and disagreement. You might see one model predicting a strong El Niño, another a weak one, and a third neutrality. The forecast becomes an exercise in weighing a collection of divergent opinions. The current situation, however, is a stark departure from this norm. We are witnessing something far rarer: independent systems built by different teams with different methods, all arriving at the same uncomfortable conclusion. This extraordinary convergence is happening at a time that should, by all accounts, make us more cautious, a period known to climatologists as the spring predictability barrier. This technical-sounding phrase describes one of the most challenging realities in atmospheric science. Every year, between roughly February and May in the Northern Hemisphere, the ability of climate models to accurately forecast El Niño events drops to its lowest point. The statistical skill of these forecasts diminishes significantly, making them little better than a random guess. This is not a flaw in the models themselves, but a reflection of a real-world process. During the boreal spring, the physical coupling between the tropical Pacific Ocean and the atmosphere above it is at its weakest. This means the signal the models are trying to detect is fainter and more easily lost in the background noise of natural variability. Forecasters are well aware of this limitation, and history is filled with examples of compelling spring forecasts that simply failed to materialize by autumn. The question now is whether this forecast, with its unprecedented model agreement, will be the one that breaks the pattern. A curious situation is unfolding in the world of climate science. Two of the planet's most reliable modeling systems are converging around a forecast for a super El Niño, yet this forecast is emerging during a period when such predictions are known to be statistically least reliable, and it begins from an oceanic state that currently registers as neutral. Under normal circumstances, this combination of factors would demand significant hesitation and numerous caveats. Instead, the International Research Institute for Climate and Society at Columbia University, or IRI, which produces one of the world's most referenced ENSO probability forecasts, is already showing an El Niño probability of roughly 70%. This figure is projected to climb toward 90% or even higher as the year unfolds. Such a strong consensus, originating from a neutral ocean state during the spring predictability barrier, is anything but ordinary. The reason this anomaly commands our attention is not due to an inherent fascination with Pacific sea surface temperature charts, though their implications are indeed profound. The true significance lies in a peer-reviewed paper published in the Journal of Climate in 2018 by Singh and his colleagues. This study did something the broader climate conversation has yet to fully process. It looked back at the most severe drought in recorded human history, an event spanning from 1876 to 1878. Using modern climate attribution science, the researchers determined its precise cause. They discovered it was not merely an El Niño, but a highly specific alignment of three ocean basins acting in concert, amplifying one another's effects into an event the climate system had not produced before and has not fully replicated since. As of the spring of 2026, all three of these basins are beginning to shift in the very direction described in that paper, raising a critical question about what this historical pattern might mean for our future. It is essential to approach this topic with caution, as prudence is the only honest way to discuss such a matter. We are not living in 1877. The oceanic alignment is not yet complete, and the models themselves contain significant uncertainty. The spring predictability barrier is a very real and relevant factor, and there are numerous plausible ways this forecast could ultimately fail to materialize. It must be stated clearly that no one in the peer-reviewed scientific community is currently forecasting a famine or suggesting that 50 million people are at risk. That is not the nature of this warning. Instead, this is something more specific and in some ways more disquieting. It is the recognition that the current data from ocean temperatures and subsurface heat content to the trend lines in each basin is arranging itself into a configuration that science has explicitly identified as the mechanism behind the deadliest climate event of the modern era. While the mainstream discussion surrounding the coming El Niño is almost entirely centered on whether it will occur and how strong it might be, very few are asking the question that the Singh paper makes unavoidable. What happens if the other two basins finish their alignment? That is the true subject of this exploration. This is not a prediction of catastrophe, nor a claim that history is destined to repeat itself. It is, rather, a careful and honest examination of a pattern that climate science urges us to take seriously, a pattern that is quietly forming in the data right now, while the public discourse remains focused on more immediate concerns, like whether we will have a dry summer. So, let us begin with the number that the models are converging toward. Once we understand what that figure represents and its place in the historical record, the gravity of the situation becomes much clearer. A reading of positive 2.1 degrees Celsius doesn't immediately sound alarming. It seems like the kind of technical detail one might find in the fine print of a meteorology textbook or on a chart scrolling by during a morning weather report. It has the feel of a small, decimal point problem, the domain of scientists, rather than something that affects the world we live in. But in the context of the Niño 3.4 index, that number is not a minor issue. It represents the threshold at which the Pacific Ocean transitions from being a background condition of the global climate system to an active force that fundamentally reorganizes it. And right now, the models are not just approaching that threshold. They are projecting that we will cross it, pass through it, and potentially push far beyond it before the event reaches its peak. To grasp the forecast's meaning, we must first understand its structure. In any major climate modeling system, the model is not run just once. It is run dozens, sometimes hundreds of times, with each iteration beginning with slightly different initial conditions. This process is designed to sample the full range of outcomes that the system's physics will permit, given the current state of the ocean and atmosphere. This collection of all individual runs is known as an ensemble. The spread of the ensemble provides a crucial piece of information: how much confidence we should have in the central forecast. A tight ensemble, where most runs cluster near the same value, suggests that the outcome is strongly determined by current conditions. A wide ensemble, however, where the runs scatter across a broad range of values, indicates that the system is sensitive and uncertain. with small initial differences leading to vastly different outcomes. It is a way for science to quantify and visualize uncertainty. The CFSV2 ensemble currently shows a central estimate, the average of all its runs of somewhere between positive 2.1 and positive 2.2 degrees Celsius in the Niño 3.4 region at its peak. However, the ensemble members are not all clustered neatly around this average. The upper tail of the distribution, which represents the runs producing the warmest outcomes, is reaching values between positive 2.5 and positive 3 degrees Celsius in some iterations. While these high-end scenarios are not the most probable outcome, they cannot be dismissed, as they represent possibilities within the model's own physics. The existence of this upper tail is significant because, in the history of ENSO forecasting, the upper tail of the CFSV2 ensemble has, on occasion, proven to be correct. This is where a comparison with historical Super El Niño events becomes critically important, because context is everything when trying to assess what a number truly means. The powerful 1982 to 1983. El Niño, for instance, peaked at approximately positive 2.2 degrees Celsius in the Niño 3.4 index. This historical benchmark gives the current forecast a tangible and sobering weight. The 1997 to 1998. El Niño was, at the time, the most powerful event on instrumental record, producing severe disruptions to global weather patterns. Peaking at an anomaly of approximately positive 2.4 degrees Celsius, it brought catastrophic drought to Indonesia, Australia, and parts of Africa, while simultaneously unleashing devastating floods across South America and East Africa. The economic toll was estimated in the tens of billions of dollars. Later, the 2015-16 event matched, and by some measures even exceeded, this historic benchmark. But it did so in a world already about 1 degree Celsius warmer than the pre-industrial baseline, meaning the absolute sea surface temperatures were correspondingly higher. Current forecasts now project a peak between positive 2.1 and 2.2 degrees, with a possibility of 2.5 or more. This places the impending event in the same magnitude class as those prior Super El Niños. This comparison is not reassuring, especially because the 1997-98 event, the one scientists use as a reference case, did not feature the multi-basin configuration that researcher Singdahl identified in the 1876-78 event. That earlier El Niño was devastating, but it was one basin acting mostly alone, a detail that complicates our understanding of what may lie ahead. There is a critical detail hidden within the acceleration pattern shown by the climate models, a clue that speaks to the physical engine driving this event. The forecast trajectories are not illustrating a slow, linear progression from a neutral state to a Super El Niño. Instead, they depict a pattern of rapid warming projected for the middle of 2026, culminating in a peak during the late autumn and early winter of the Northern Hemisphere. This signature of swift acceleration is physically significant. It strongly suggests that the event is not being driven by the whims of the atmosphere, by random fluctuations in wind that happen to warm the ocean's surface. Rather, the driving force appears to be the ocean itself. The heat is already stored deep below the surface of the Western Pacific, and it is being unleashed by a mechanism that, once initiated, the climate system almost always completes. This distinction is crucial for understanding the forecast. It is also important to address the question of model bias, a legitimate concern that should not be dismissed. The CFSV2 model, for example, is known to have a tendency to forecast El Niño peaks that are higher than what ultimately materializes. This is a documented characteristic, and professional forecasters are aware of it, applying a mental correction when they analyze its output. If the model predicts a peak of 2.2 degrees, An experienced analyst might adjust that down to somewhere around 1.8 or 2 when forming a consensus. This is a real and appropriate caveat. However, what sets this particular situation apart is the North American Multi-Model Ensemble, or NMME. This is not a single model, but a collection of multiple, independently developed systems from various institutions, including the Canadian Meteorological Centre, the National Centres for Environmental Prediction, and GFDL. Each is built with different code and different assumptions about ocean-atmosphere interaction. Crucially, these models do not share the same biases. When they all begin to agree with each other, and with CFSV2, this convergence is not the echo of a single model's quirk. It is independent, physics-based systems arriving at the same conclusion. Right now, the NMME ensemble mean is tracking remarkably close to the CFSV2 central estimate. In climate science, there is a concept known as the signal-to-noise ratio. It describes the degree to which a predictable climate pattern stands out from the background chatter of natural variability. During a period known as the spring predictability barrier, noise is typically high and the signal is low, making forecasts made during this window historically unreliable. What makes the current situation so anomalous is not just that the models are in agreement, but that this consensus is emerging at a time when noise should be overwhelming the signal. The fact that a clear pattern is managing to break through this period of statistical chaos suggests that the signal itself must be exceptionally strong. This is not a guarantee, but it is a powerful indication. This strength, this persistence through a window that typically erases weaker signals, points us back to the same place, the deep ocean subsurface, where the energy for this event is already stored, already waiting, and already in motion. The scale of this potential change is staggering. The current anomaly in the Niño 3.4 region is a mere plus 0.16 degrees Celsius. The central estimate from the models for the peak anomaly, however, is around positive 2.1 to 2.2 degrees. This means we are contemplating a potential warming of more than 2 degrees Celsius in a single ocean region over just 6 to 8 months. In a climate system where shifts of 1/10 of a degree can trigger significant global impact. A 2-degree acceleration in the Central Pacific is not a minor fluctuation. It is a profound reorganization. The immense energy required to drive such a change is already present in the water. It simply has not yet reached the surface. This brings us to a part of the story that is receiving almost no attention, a reality where the ocean has, in a sense, already broken first. What you see on the surface of the Pacific right now is a neutral ocean, a deceptive calm, but what lies beneath is an entirely different story. This is a case where the surface appearance of a system is almost the opposite of its true condition, like a frozen lake that looks solid until a single step reveals the cracking ice below. The Oceanic Niño Index, the number that appears in news headlines, is a surface measurement. It tells you what the top layer of the Pacific is doing, but it reveals nothing about what is happening 100 or 200 meters down. The real story is unfolding in this hidden realm, in the vast warm water reservoir that scientists call the subsurface heat content of the Western Pacific. Understanding what is happening there is the key to why the surface models are forecasting what they are. The Western Pacific Warm Pool, an immense region of ocean situated roughly to the east of the Philippines and northeast of Australia, is one of the warmest expanses of open water on the entire planet. Under normal conditions, sea surface temperatures in this area consistently run between 29 and 30 degrees Celsius. This vast reservoir of thermal energy acts as the primary engine for much of the Pacific's climate system, and its current state holds vital clues to our future. The warmth building in the Pacific Ocean might feel like a planetary fever, but its true origins are hidden. During a La Niña phase, the counterpart to El Niño, persistent trade winds sweep across the water, pushing the warm surface layer westward. This action functions like a colossal pump, causing heat to pile up and sink deep into the western Pacific. There, it becomes a vast thermal battery, stored in the subsurface, where it is insulated from the atmosphere and cannot easily release its energy. In the early months of 2026, surface waters in this region were observed at 29 to 30 degrees Celsius, near the thermodynamic ceiling for tropical oceans. But the most critical measurements are coming from below, gathered by Argo floats and the TAO Triton array. These sensors show significant positive temperature anomalies deep underwater. The heat is there, and it is beginning to stir. The next phase of this process is driven by equatorial Kelvin waves. These are not crashing breakers, but immense, slow-moving disturbances deep within the ocean, propagating eastward along the equator at 2 to 3 meters per second. They exist as a pulse of warmth within the thermocline, the boundary layer, where temperature drops sharply with depth. When the trade winds that held this system in check weaken or reverse, the vast reservoir of warm water is released. This warmth does not surge to the surface immediately. Instead, it journeys eastward as a Kelvin wave, depressing the thermocline as it goes and progressively thickening the warm surface layer. Only when these waves arrive off the coast of Peru and Ecuador does the thermocline deepen enough to warm the sea surface, producing the signature of El Niño. This visible warming is the final expression of a journey that began months before, far away and deep underwater. It is therefore useful to see El Niño not as the build-up of heat, but as its release. For months or years, the La Niña phase compresses this thermal energy into the western Pacific, like coiling a giant spring. When the trade winds falter and the system reaches its tipping point, all that stored energy begins its slow journey eastward. This reveals a profound delay in the Earth system's response. By the time the Niño 3.4 index crosses the positive 0.5 degrees Celsius threshold and an El Niño is officially announced, the event was already an inevitability. The outcome was decided months earlier by the sheer heat content of the water column and the Kelvin waves that were already in transit. This deep ocean reality is precisely why current forecast models are converging with such high confidence. These predictions are not speculative. The models are forecasting a major El Niño because they are initialized with real-world subsurface ocean data. Those observations tell a clear story. The enormous thermal energy for a large event is not just a possibility, it is already present, and it has begun to move. From our vantage point, the atmosphere may seem unaware, and the ocean surface may show little sign of the coming shift. But deep below, the accumulated heat already points toward a major warming event, and the models are simply reading that signal and projecting its conclusion. It is crucial, however, to acknowledge the genuine uncertainties that remain. The link between subsurface heat and the eventual magnitude of an El Niño is strong, but not deterministic. There are cases in the observational record where the ocean appeared primed for a major event, only for it to fall short. The years 1990 and 2014 are notable examples where significant subsurface warmth failed to translate into the powerful El Niño that indicators suggested. In those instances, the atmosphere played a decisive, suppressive role. Persistent trade winds refused to weaken on the necessary timescale, effectively acting as a brake and preventing the Kelvin waves from delivering their warmth to the surface. It is a reminder that the atmosphere can, at least temporarily, resist the ocean's push. However, the current situation appears distinguished from those past false starts by two critical factors: the sheer magnitude of the anomaly and its timing. The subsurface heat content in the Western Pacific is not just marginally positive, it is substantially above the historical threshold known to precede major events. Furthermore, the timing is key. This powerful oceanic signal is emerging as we pass the seasonal spring predictability barrier, a period of high atmospheric noise. This relative quiet allows the underlying oceanic physics to be detected by models with greater clarity. The ocean itself is indifferent to modeling challenges. The Kelvin waves are already propagating, and the heat content is already exceptionally high. The models are observing the ocean's physical state and calculating what will happen when this energy arrives. With this understanding, the central question shifts. It is no longer whether there is enough energy to drive a super El Niño. The focus now turns to atmospheric coupling. Will the atmosphere allow this oceanic energy to fully express itself at the surface? This delicate dance between ocean and atmosphere is the one element that forecasting models cannot resolve with absolute certainty. It remains the final pivotal variable. And yet, even with that uncertainty, the balance of evidence is increasingly tilted toward yes. Yet, what determines if an event becomes truly historic is not confined to the Pacific Ocean. That is the part of the equation the forecast models capture well. What distinguishes an event that merely reorganizes global climate for a season from one with catastrophic, worldwide consequences is the concurrent state of the other two major ocean basins. The simultaneous behavior of the Atlantic and Indian Oceans is the amplifier that could turn a major event into a historic one. And that is where this conversation must diverge from a standard El Niño discussion. It leads us to the concept of a triple basin alignment and to a pivotal 2018 paper by Singh and his colleagues. A particular scientific discovery often remains hidden from the public eye, never finding its way into popular lectures or television documentaries. Such was the case with a paper published in the Journal of Climate, a respected, peer-reviewed publication intended for a specialized audience of climate scientists and atmospheric researchers. Its title reads like a highly technical report, a characterization of climate forcings during the global drought of 1876 to 1878. It is the sort of name that can cause one's attention to drift before the final word is read. Yet, the research it contains is arguably one of the most vital pieces of attribution science to emerge in the last decade, and its central conclusion is profound. The catastrophic drought of 1877, which led to the deaths of 50 million people, was not caused by El Niño acting alone. While El Niño was a major factor, the true mechanism that transformed a climate event into a global disaster was a synchronized pattern across three distinct ocean basins. This convergence amplified each region's drought signal into a force far greater than any single ocean could have produced on its own. Understanding this distinction is essential, as it helps explain why the current state of our oceans is so concerning in a way that a simple El Niño forecast is not. The first part of this climatic puzzle, the Pacific component, is the one most people are familiar with. An El Niño event in the central and eastern Pacific is known to suppress rainfall across a vast portion of the tropics and subtropics, affecting South and Southeast Asia, Australia, Sub-Saharan Africa, and areas of the Americas. This occurs because of a disruption to a massive atmospheric circulation pattern known as the Walker circulation. Under normal conditions, this circulation carries moisture-rich air westward across the Pacific, where it rises over the warm ocean pool, generates rain, and then returns eastward at high altitudes. But when El Niño warms the central Pacific, the warmest waters shift eastward. The rising column of air in the Walker circulation follows this shift, leaving the regions that typically receive this life-giving moisture in what is known as a subsidence zone, an area where air descends, effectively suppressing the formation of rain. This Pacific piece of the puzzle is a well-documented and dangerous phenomenon in its own right. However, the Pacific's influence by itself cannot fully account for the devastation of 1877. While the El Niño of 1876 to 1878 was indeed powerful, modern estimates suggest it was likely not significantly stronger than the event that occurred from 1997 to 1998. The fact that it became a global catastrophe indicates that the Pacific was not the sole driver of the event. A second, crucial piece of this climate puzzle was unfolding in the Indian Ocean. This component is known as the Indian Ocean Dipole, or IOD, which is a mode of climate variability that functions in a way somewhat analogous to El Niño. During its positive phase, when the western Indian Ocean becomes unusually warm compared to the eastern part, the IOD profoundly alters the behavior of the South Asian monsoon. This monsoon is the agricultural lifeblood for nations like India, Pakistan, and Bangladesh, as well as much of Southeast Asia, delivering the vast majority of annual rainfall to a region that sustains roughly 2 billion people. When the Indian Ocean Dipole is in a positive state, the atmospheric circulation above the ocean reorganizes. This change weakens the flow of moisture toward the Indian subcontinent, which in turn reduces monsoon rainfall and elevates the risk of drought across South Asia during the critical June to September season. The simultaneous occurrence of a positive IOD and a strong El Niño does not simply create an additive effect on their individual drought impacts. Instead, their atmospheric teleconnections, the large-scale patterns through which ocean temperatures influence the atmosphere far away, begin to interact. In certain configurations, these patterns reinforce one another, producing droughts far more severe than either event could cause alone. In 1877, the Indian Ocean Dipole was in a strongly positive phase, and the result was a catastrophic failure of the monsoon. Crop failures across India were not merely partial, they were nearly total in major agricultural zones. While British colonial policy tragically ensured that the ensuing famine was far deadlier than the drought itself, the physical trigger for the agricultural crisis was this double forcing, with the Pacific and Indian Oceans acting in concert on the very atmospheric circulation the monsoon relies upon. The third component of this devastating alignment originated in the North Atlantic. This is the element that typically receives the least attention in standard discussions of El Niño. Yet the scientific paper found it to be a profoundly underappreciated amplifier. In 1877, sea surface temperatures in the North Atlantic were anomalously warm. This warming exerted a measurable influence on global atmospheric circulation through a complex set of teleconnections that climate scientists are still working to fully understand. The Atlantic's influence on the water circulation operates through a different pathway than that of the Indian Ocean. It alters the distribution of moisture in the upper troposphere, modifies the position of the subtropical jet streams, and shifts the large-scale pressure patterns that determine where rain does and does not fall across Africa, South America, and the Americas. Viewed in isolation, the Atlantic warming of 1877 would not have been sufficient to trigger a catastrophic drought. However, when combined with a powerful Pacific El Niño and a positive Indian Ocean Dipole, it acted as a third reinforcing force. It was an additional finger on the scale, tipping an already precarious global moisture balance toward disaster. The cumulative effect of all three ocean basins acting in unison was something that paleoclimate records, such as tree ring reconstructions, describe as the most severe drought in at least 800 years, and possibly even longer. The failure of monsoons across Asia, the simultaneous collapse of rainfall in sub-Saharan Africa and Brazil, and the synchronized crop failures across multiple continents. All of these events trace back to this triple alignment. These regions, sharing no common borders or modern supply chains, were connected by a single powerful force, their shared climate system, which had created a globally coherent drought pattern that no single ocean basin could have generated on its own. This brings us to the year 2026, and to the central question that this historical analysis raises. The answer is not one to be buried in qualifications. The Pacific Ocean is currently warming, and climate models are projecting the development of a super El Niño. This means one part of the historic alignment is actively forming. At the same time, the Indian Ocean is showing a trend toward a positive IOD phase. Current sea surface temperature patterns. Specifically, the temperature differential between the western and eastern Indian Ocean are displaying the early structure of a positive IOD. This does not guarantee that the IOD will lock into a strongly positive phase, but the initial signs are undeniably present, raising a critical question about what the future may hold. The seasonal evolution of the Indian Ocean Dipole is such that its influence typically reaches a zenith during the autumn months of the Northern Hemisphere. This timing is critical, as it is precisely when El Niño is also approaching its own peak. Should both of these powerful climate systems crest at the same time, their distant effects, or teleconnections over South Asia and Africa, would likely compound one another rather than cancel each other out. Meanwhile, the North Atlantic is currently observed to be anomalously warm, a present-day reality, not a future forecast. For the last 2 years, sea surface temperatures there have been at historically elevated levels. The scientific community is actively debating the reasons for this warmth, with some researchers pointing to reduced aerosol emissions following new shipping fuel regulations, while others suggest long-term ocean heat accumulation or natural variability. For our purposes, however, the debate over the cause is less important than the observable condition itself. The North Atlantic is warm, it has been for some time, and there is little evidence to suggest it will cool dramatically in the near future. This confluence of factors presents a sobering picture. The Pacific Ocean is on a warming trajectory that points toward a super El Niño. The Indian Ocean is trending toward a positive IOD, and the North Atlantic is already exceptionally warm. What we are witnessing, then, is not a certainty, but a troubling convergence of warning signs. This is not yet the full alignment seen in the historical record. The IOD has not fully committed. The ultimate magnitudes of these events remain uncertain, and the atmospheric coupling between the ocean basins is a complex process that defies deterministic prediction. There are many ways this configuration could fail to replicate the 1877 setup, and yet the directional trend across all three basins is simultaneously pointing toward the very mechanism that researchers like Singh and his colleagues identified as the driver behind the most severe climate catastrophe of the modern era. The mainstream conversation surrounding the current El Niño forecast is almost entirely centered on the Pacific. It tends to focus on questions of its potential strength, its peak timing, and which specific regions will face drought versus flooding. These are, of course, legitimate and vital questions. This narrow focus, however, may be overlooking a much larger, interconnected threat. The science of 1877 makes a different question unavoidable. The issue is not merely whether a super El Niño will manifest in the Pacific. The far more critical question is whether a super El Niño will emerge in the Pacific times, while times the Indian Ocean simultaneously amplifies monsoon failure, and times the North Atlantic adds its own weight to the disruption of global circulation. This is because that compound configuration, what some researchers have started calling teleconnection stacking, is not simply the sum of three distinct climate events. It represents something qualitatively different from any one of them in isolation. It is the mechanism that can transform a climate anomaly into a system-level disruption. The event itself remains uncertain. The individual signals from each ocean basin are uncertain. The coupling between them is uncertain. But the very configuration that science has explicitly identified as the mechanism behind 50 million deaths is beginning to assemble. And the forecast that most people are watching, the one focused on El Niño's arrival and scale, is only telling a fraction of the story. It describes just one of the three instruments in this ominous ensemble, while the other two are already tuning up. Part 5. The 1877 event reconstructed. There is a way of discussing historical climate catastrophes that makes them feel distant and abstract. We can frame them as disasters that befell people in a different technological epoch, whose deaths seem like a predictable consequence of pre-modern vulnerability. It is a framing that is tragic, yet somehow separate from anything we might need to worry about today. But to truly grasp the stakes, we must resist this comfortable temptation. Because in this case, that framing is profoundly wrong. The event of 1876 to 1878, sometimes called the Great Drought, the Victorian Great Famine, or known by regional disasters like the Grande Seca in Brazil, was not a collection of local events dressed up in global language. It was a genuinely global climatic disruption that simultaneously affected every inhabited continent. The significance of this event lies not in any single disaster, however severe, but in its breathtaking synchronicity, which made it catastrophic in a way no regional drought could ever replicate. To comprehend the scale of this event, one must begin with the monsoon. In 1876, the South Asian monsoon, the seasonal rainfall system that delivers about 80% of India's annual precipitation between June and September, did not simply weaken or underperform. Across large portions of the subcontinent, it collapsed. Rainfall, in some regions, fell to less than 25% of normal levels. This failure extended not just for one season, but for 2 consecutive years. As 1877 repeated the drought that 1876 had initiated. For a subcontinent with a population between 250 and 300 million people, the majority of whom were subsistence farmers wholly dependent on that rain for their food, 2 back-to-back failed monsoons did not just stress the agricultural system, it meant the destruction of it simultaneously. And that word simultaneously is doing enormous work here. At the same time, the rainfall systems across China's Shaanxi, Henan, and Shandong provinces also failed. The Yellow River Basin, the agricultural heartland for one of the world's most densely populated regions for millennia, experienced drought conditions of a severity that tree ring records suggest had not been seen in at least 3 to 4 centuries. The death toll in China alone from this period, sometimes called the Incredible Famine or Dingwu Qijin, is estimated by historians to be between 9 and 13 million people. That single estimate is larger than the total military deaths suffered by the United Kingdom during the entire Second World War. And this catastrophe was still only a part of the global picture. Across sub-Saharan Africa, the rainfall systems that numerous communities and agricultural societies relied upon failed within the same 1876 to 1878 window. In Brazil, the Nordeste region, the semi-arid interior known as the Sertão, endured what became known as the Grande Seca, or the Great Drought. This was a rainfall failure so severe and prolonged, lasting 3 years, that it killed an estimated 500,000 people in a region of only a few million. It also triggered mass migrations toward the coast that would reshape the human geography of Brazil for generations to come. The pattern of devastation continued to repeat itself across continents. In southern Africa, on the Deccan Plateau of India, and along the coastal regions of East Africa, the same story unfolded with regional variations. Rainfall failures led to crop losses, which led to hunger and death. These were not isolated tragedies, but interconnected pieces of a single, worldwide climatic event. It is the global simultaneity of all these occurrences that the paleoclimate record so starkly confirms. By measuring the growth rings of ancient trees, scientists have assembled a detailed record of drought and moisture stretching back for centuries. Data gathered from sites across Asia, the Americas, Africa, and Australia all point to a singular conclusion. The period from 1876 to 1878 witnessed one of the most globally coherent drought events in at least 800 years of reconstruction. This event was not necessarily the most severe in any one location, but it was unique in its synchronization. Across the most distant corners of the planet, the climate signals all aligned, telling the same story of drought at the same time. Such planetary alignment was no coincidence. As researchers have documented, it was the unmistakable fingerprint of a specific ocean pattern across multiple basins, which imposed a common state of drought upon climate systems around the world. In 1876, the world's population stood at roughly 1.4 billion. The famines triggered by this climate event between 1876 and 1879 are estimated by historians, most prominently Mike Davis, in his 2001 work, to have claimed between 30 and 50 million lives. This wide range reflects the grim realities of the era. Historical records in many affected regions are fragmented, and separating deaths from pure starvation versus famine-related disease is a difficult task. Furthermore, the political priorities of colonial administrations often meant that precise record-keeping was not a primary concern. Yet, the numbers remain staggering. Even the lower estimate of 30 million represents about 2% of the entire human population at the time, while the upper estimate of 50 million approaches 3.5%. In absolute terms, outside the global wars of the 20th century, no other single event in recorded history has resulted in such a catastrophic loss of life. It is here that the threads of this story converge into a stark warning. This devastating outcome was not the result of a typical, albeit severe, El Niño. Instead, it was driven by that specific, rare alignment of ocean patterns across the Pacific, the Indian, and the North Atlantic. This multi-basin event forced simultaneous drought across nearly every major agricultural system on the planet. The climate created the physical conditions for a global harvest failure. The synchronization across oceans ensured that there were no unaffected breadbaskets elsewhere in the world to provide relief. But it was the human systems layered on top the structures of governance, colonial policies, and trade networks that ultimately determined who would survive and who would perish in this crisis. The difficult truth of the 1876 to 1878 famines is that while the climate made them possible, it was human systems that made them so profoundly lethal. This is not a simple conclusion, nor does it absolve either the natural event or the institutions that managed its consequences. However, it is the argument upon which the most thorough historical and economic scholarship of this period has converged. Understanding this distinction is absolutely essential, as it reveals why calculating the risk of a modern-day equivalent is far more complex than simply scaling the 1,877 death toll to today's global population. In his exhaustive study of this era, the historian Mike Davis referred to these events as the late Victorian Holocausts. His choice of the word Holocausts was quite deliberate. He argued that the immense scale of death was not merely the product of a drought. Rather, it was the direct result of a specific economic and political system, primarily British colonial administration in India and in various forms across Africa and Asia, that had rendered entire populations exceptionally vulnerable to climate stress and then catastrophically failed to offer any meaningful mitigation. To understand this failure, one need only look at the specific mechanisms at play in British India. The colonial government, operating under the prevailing economic orthodoxy of the time, a rigid form of laissez-faire market theory, insisted that government intervention in food markets was both economically harmful and morally corrupting. Consequently, even as the famine raged, the government maintained the export of grain from India. Historians return to this detail time and again because it so perfectly encapsulates the policy logic of the period. While millions of people in India were starving, grain continued to leave Indian ports for British and other international markets. The reason was simple. The price in those export markets was higher than the purchasing power of starving farmers in the interior. The food was physically present, but the logic of the market dictated it would go elsewhere. The railroad network, which the British had constructed across India in the preceding decades for military and resource extraction purposes, played a perverse role in the crisis. During the famine, it did not primarily function as a network for distributing relief. Instead, it became a highly efficient mechanism for price arbitration. Grain dealers used the railways to move food toward the higher-priced urban and coastal markets, which in practice meant moving it away from the desperate famine zones where subsistence farmers had lost all purchasing power. In this context, the railroad, a symbol of modernity, actively accelerated the extraction of food from the very regions that needed it most, sending it toward markets that could simply pay more. Where British famine relief policy did exist, it was frequently designed to minimize costs and avoid creating what administrators termed dependency among the population. Relief camps were established, but they were deliberately understaffed and undersupplied. As Mike Davis notes, with stark severity, food rations in some of these camps were calculated at levels below those provided to inmates at the Auschwitz concentration camp. The political will to intervene on a scale that matched the human crisis was entirely absent. This was not merely an oversight, it was a consequence of an ideological framework that found mass death by market forces more acceptable, or at least more philosophically consistent, than the alternative of direct market intervention. The catastrophe was not confined to the British Empire. The situation in Qing China was structurally similar, even if the political causes were distinct. There, the Qing dynasty, which had already been weakened by decades of internal conflict and external pressures, simply lacked the administrative capacity and the financial resources to respond to a drought of this magnitude across its northern provinces. It represents a different form of systemic failure, not one of ideological rigidity, but one of a state apparatus too fragile to cope with a crisis on such an overwhelming scale. In centuries past, traditional systems for famine relief, however flawed, had provided a buffer against catastrophe. But by the mid-19th century, these networks had been fractured by immense upheavals, including the devastating Taiping Rebellion. The climate crisis of that era, therefore, did not strike a resilient society, but one whose state apparatus was already profoundly weakened, leading to a tragically predictable outcome. Why does this history, from 1877, resonate so powerfully for a year like 2026? The answer lies in a crucial insight from the Singh et al. Paper, which makes explicit what purely climate-focused models often leave unsaid. The study suggests that the 50 million people who perished were not victims of a climate event alone. Their deaths were the result of a devastating combination, a synchronized global stress event created by the climate and human systems that were either incapable of managing that stress or were actively designed to ignore it for the most vulnerable. The climate applied the pressure, but it was the design of human institutions that determined whether that pressure was absorbed safely or allowed to crush entire populations. This historical lesson forces us to ask a difficult question about our own time. Our modern global system is, of course, equipped with different institutions. We have international food aid organizations, global commodity markets, sophisticated early warning systems, and national governments with a far greater capacity to respond than the colonial administrations of the Victorian era. These systems are significant, and they genuinely reduce the risk of mortality on the scale seen in the 1870s. A direct repetition of 1877 is not the most likely outcome of a verified triple basin climate alignment in 2026. However, The more pressing question is not whether our institutions can prevent a mirror image of the past. The more urgent inquiry is whether these modern systems, with their extraordinarily interconnected global food supply chains, commodity markets that transmit price shocks worldwide in mere hours, and political systems highly sensitive to rising food costs, can endure a synchronized global drought without introducing their own new and distinct points of failure. And to that question, the answer is far from comfortable. The Victorian system collapsed under the stress of 1,877 inches, ways that were characteristic of its very nature: a reliance on colonial extraction, a rigid devotion to market orthodoxy, and a deliberate exclusion of human welfare from the calculus of governance. A modern system would not fail in precisely those ways, but it could certainly fail in others. The scenario described by Singh and his colleagues represents a stress test of a magnitude that our current global framework has never been subjected to since its construction. It is a trial by fire for a system that has never truly been tested at full scale. We will return to what that test might look like in our contemporary world, but first, we must examine the engine driving it, the specific mechanism that most analyses miss. This brings us to the crucial detail in the Singh et al. Analysis that is most relevant to the data we see today, and explains why the standard El Niño forecast tells only part of the story. Perhaps the single most important sentence in the 2018 Singh et al. The paper is not the one detailing the death toll. It is a more technical but unambiguous declaration that the sheer magnitude and global reach of the 1,876 and 78 drought cannot be recreated in models using forcing from the Pacific Ocean alone. This statement is the key to understanding why the entire forecast situation requires a new frame of reference, one that looks beyond the standard El Niño analysis. If that sentence is correct, and the paper provides substantial evidence that it is then focusing exclusively on the Pacific component, as most mainstream discussion does, is not merely incomplete. It is fundamentally missing the core mechanism. It is akin to measuring the fuse while ignoring the powder keg. To grasp the full picture, we must look to the Indian Ocean Dipole, or IOD. The IOD is not simply a patch of warm water. It is a coupled ocean-atmosphere phenomenon, meaning the ocean and the atmosphere are locked in a feedback loop, each reinforcing the other's behavior. When the western Indian Ocean becomes unusually warm compared to the eastern part, the atmosphere above it responds, altering patterns of wind and moisture transport. These new wind patterns, in turn, help maintain the very sea surface temperature gradient that created them. The result is a self-sustaining state that, once established, tends to persist through the northern hemisphere's autumn. The atmospheric effect of a positive IOD on the South Asian monsoon is profound, operating through a mechanism known as the anomalous Walker circulation over the Indian Ocean. Under normal conditions, the monsoon is driven by a circulation that pulls moisture from the ocean onto the Indian subcontinent, fueling the towering thunderstorms that deliver the bulk of the region's rainfall. But in a positive IOD state, this process is disrupted. The anomalous atmospheric circulation weakens the low-level winds carrying moisture ashore and simultaneously strengthens conditions that suppress the deep convection needed for rain. The outcome is a reduction in monsoon rainfall, a reduction that can be dramatic, depending on the intensity of the IOD. Now, let us add the influence of a Pacific El Niño. El Niño independently suppresses the Indian monsoon through a related but distinct mechanism. It alters the Walker circulation over the Pacific Ocean, which in turn changes large-scale pressure patterns across Asia, also weakening the monsoon. Both the IOD and El Niño push the monsoon in the same direction toward drought, but they do so through partially separate physical pathways. When both of these powerful phenomena are present at the same time, their effects are not simply additive. The large-scale atmospheric patterns they modify, the the Walker circulation, the subtropical ridges, the placement of pressure systems begin to interact. In the specific configuration of a strong positive IOD coinciding with a strong Pacific El Niño, the resulting atmospheric state becomes qualitatively different from what either signal could produce alone. Climate scientists have a term for this: teleconnection stacking. When multiple ocean-based forcing signals stack their atmospheric impacts over the same region and in the same direction, the resulting climate anomaly can be disproportionately larger than what any single driver would suggest. A third influence, originating from the Atlantic, operates through yet another mechanism, one that is more indirect and requires careful explanation. The surface temperatures of the North Atlantic Ocean play a pivotal role in shaping global atmospheric circulation. This influence is exerted through the ocean's effect on the Atlantic Intertropical Convergence Zone, or ITCZ, a band of intense convection and rainfall that travels seasonally across the equatorial Atlantic. When the North Atlantic becomes unusually warm, the ITCZ has a tendency to shift northward. This, in turn, alters the large-scale patterns of moisture transport over both South America and Africa. It's a complex chain reaction that doesn't stop there. This warmth also affects the Walker circulation over the Atlantic, which is itself connected to the Pacific's Walker circulation through the continuous flow of the global atmosphere. In effect, anomalous warmth in the North Atlantic introduces a third powerful force to a system already being distorted by a Pacific El Niño and the Indian Ocean Dipole. The resulting state of the atmosphere is one where the very moisture systems that sustain agriculture across several continents are simultaneously displaced, weakened, or suppressed. This is the core of the compound climate event framework, a concept that represents one of the most significant advances in climate science in the last decade. Traditionally, climate risk assessment has approached these hazards individually. Analysts would ask about the probability of a strong El Niño, or a positive Indian Ocean Dipole, or anomalous warmth in the North Atlantic, treating each as an independent risk to be added together. However, analysis from researchers like Singh and their colleagues, consistent with a growing body of research on compound events, reveals a more interconnected reality. These hazards are not independent at all. They can, in fact, co-occur and even reinforce one another. When they do, the resulting impact is not merely the sum of their individual effects, but something far greater. This multiplicative effect is precisely what unfolded during the devastating events of 1877, raising the question of how we should redefine risk in a deeply connected world. What makes our current situation historically unique is that modern climate datasets and modeling systems are, for the very first time, capable of detecting the early formation of such a triple basin alignment in near real time. This capability simply did not exist in 1877. There was no global observational network, no Argo floats profiling the deep ocean, no satellites measuring sea surface temperature, and no moored arrays transmitting subsurface data. There was no way to see the Indian Ocean Dipole developing, the North Atlantic warming, or the subsurface Kelvin waves traveling eastward across the Pacific in time to react. The configuration simply assembled itself and unleashed its full impact before any human system could anticipate it. Today, we have the tools to see it coming. We now possess the data, the models, and the attribution science to understand these complex interactions. What we seem to lack, however, is a mainstream scientific communication infrastructure that can translate a multi-basin compound event analysis, the specific kind of work pioneered by Singh, into the public forecast conversation in a way that reflects its profound importance. The standard El Niño forecast products the public sees are, by design, focused on the Pacific. The Indian Ocean Dipole receives its own forecasts, but they garner only a fraction of the public attention. Meanwhile, the North Atlantic's sea surface temperature is typically discussed in the context of hurricane seasons, but rarely in terms of its interaction with these other massive climate signals. The consequence of this fragmented approach is a situation where the most critical aspect of the current climate forecast is rendered almost invisible in the mainstream discussion. This hidden element is not the Pacific El Niño alone, but the potential assembly of that specific multi-basin configuration identified from the 1877 event. This alignment may not fully materialize, of course. The Indian Ocean Dipole might not lock into a strongly positive phase, or the Atlantic may not couple with the Pacific El Niño in the precise way the historical record shows. All of these outcomes are possible, and some may even be probable. The challenge lies in communicating this complex uncertainty without diminishing the significance of the threat. Yet, the mere possibility that this assembly is happening right now, detectable in our data for the first time in history, precisely because we have the observational systems that 1877 lacked, is a reality that deserves a more prominent place in our global conversation. If this configuration does fully materialize, the question is not whether the world will look exactly like it did in 1877. Instead, we must ask whether the world of today, with all its modern systems, capabilities, and unique vulnerabilities, is prepared for the kind of stress test this alignment represents. The modern world is not the Victorian world, but it is certainly not immune to synchronized global climate disruption. It is simply vulnerable in different, and in some ways, more intricate ways. Here is a concept that is simple to state, but far more difficult to fully internalize. The baseline has shifted. Every El Niño that occurs from this point forward will unfold in a climate that is fundamentally different from any that occurred before, roughly 2015. This is not a slight difference, nor a marginally warmer background state. It is a measurably, physically distinct climate system. The baseline sea surface temperatures, the atmosphere's moisture content, the conditions on land, and the thermodynamic limits on extreme events have all been altered relative to the pre-industrial reference state that scientists use to define what is normal. Currently, the global mean surface temperature is running approximately 1.2 to 1.5 degrees Celsius above that pre-industrial baseline. The average that existed before large-scale fossil fuel use began changing our atmosphere's composition. That number can sound small, in the same way that a plus 2.1 degrees Celsius reading in the Niño 3.4 index might seem minor. But just as the Niño index number reveals its immense power once you understand its impact on global atmospheric circulation, the global warming baseline stops sounding small once you grasp what it means for the behavior of climate events operating within this new reality. Consider the most fundamental thermodynamic implication. Our atmosphere holds water vapor, which is the fuel for all rainfall and storms. This is governed by a physical relationship known as the Clausius-Clapeyron equation, which states that for every 1 degree Celsius of warming, the atmosphere can hold approximately 7% more water vapor. 7% more water vapor translates directly to 7% more fuel available for precipitation events, leading to heavier rainfall where rain is already expected. But, and this is the crucial detail for understanding drought risk, it does not mean more rainfall everywhere. A warmer, thirstier atmosphere can also draw more moisture away from dry regions, intensifying droughts elsewhere and creating a world of greater extremes. An increase of water vapor in the atmosphere has a polarizing effect, simultaneously intensifying both the world's wet and dry regions. This means that areas prone to rain tend to receive more, while arid areas tend to become even drier. An El Niño event naturally creates this contrast through its effects on global atmospheric circulation. But a warmer atmosphere, with its greater capacity for moisture, amplifies this divide. In practical terms, This suggests that a super El Niño in 2026 would cast a drought signal over the same parts of the globe that were affected in 1877, South Asia, Sub-Saharan Africa, and northeastern Brazil. The critical difference, however, is that it would occur within a background climate where the potential for extreme dryness is already much higher than it was in the Victorian era. The soil moisture deficits that form during El Niño-driven droughts become deeper when they begin from an already depleted baseline. The heat waves that often accompany these droughts, a result of reduced evaporative cooling over parched land, become far more intense when layered on top of a warmer average temperature. This creates a series of feedback loops that sustain and magnify drought conditions. Dry soil leads to less evaporation, which suppresses rainfall, which in turn dries the soil further. In our warmer climate, these cycles are not only triggered more easily, but are also significantly harder to break. Climate science uses a powerful analogy to describe this phenomenon: loading the dice. The concept illustrates how human-caused warming does not guarantee specific extreme events, but it does shift the distribution of probabilities, making extreme outcomes more likely and moderate ones less so. An ordinary unloaded die might roll double sixes, representing an extreme event about 3% of the time. But a loaded die could show the same result 10% or even 15% of the time. While you can never predict an individual roll, the frequency and intensity of extreme outcomes systematically increase. Today, the climate system is playing with dice that are loaded in a way they simply were not in 1877. This means that the very same atmospheric and oceanic conditions, the same multi-basin configuration, would produce far more intense climate anomalies on the surface in 2026 than they would have in 1876. This isn't necessarily because the ocean forcing is stronger, but because the thermodynamic response of the atmosphere and land is amplified by the higher baseline temperature. It's a stark reminder that the rules of the game have changed. The ocean's heat content has risen not just at the surface, but throughout its depths. Globally, the oceans have absorbed approximately 90% of the excess heat that greenhouse gas emissions have trapped in the Earth's system since the industrial period began. This immense thermal energy is now distributed through the entire water column, meaning the power available to fuel climate extremes is greater now than at any other point in recorded history. When a Kelvin wave travels eastward across the Pacific, it moves through an ocean that is warmer at depth than it was even during the powerful 1997-98 event. When that deep, warm water finally surfaces in the eastern Pacific, it emerges into an environment where sea surface temperatures are already elevated. This results in a higher absolute temperature anomaly, not just a departure from the average, but a higher actual water temperature. Higher absolute temperatures fuel greater evaporation, loading more moisture into the atmosphere above the El Niño region and powerfully amplifying the changes in atmospheric circulation that El Niño drives. This amplification, however, does not bring uniformly negative news. The same thermodynamic processes that intensify drought in some regions also intensify rainfall in others. The areas that typically receive above-average precipitation during El Niño events, including parts of the southern United States, eastern Africa, and coastal South America, would likely see even more rain. A warmer baseline does not simply increase suffering in all directions, but this raises a critical issue of equity. As the distribution of these impacts is far from equal, the benefits of more rain and the burdens of more drought are not shared evenly, and the regions most threatened by the Singh et al. Multi-basin alignment are already among the most climate vulnerable on the planet. It is important to clarify that the central point is not that a modern climate baseline would make a 2026 event more deadly than the 1877 catastrophe in absolute terms. Our world has changed. Modern agricultural productivity, global supply chains, sophisticated early warning systems, and international humanitarian aid mean that the mortality from a synchronized global drought would not replicate the devastating rates of the Victorian era. However, the same thermodynamic amplification that loads the climate dice also means that the physical intensity of the climate signals from a verified triple basin alignment in 2026 would likely be far greater than those that produced the 1,877 event. The stress placed on our modern agricultural systems and food supply chains, which were built and optimized for the climate of the last century, not the one we are entering, would be correspondingly more severe. And whether these modern systems can absorb that greater stress without triggering cascading failures is a question that no climate model can definitively answer. Part 9. The global food system is a single machine. In 1877, the world's food systems were not interconnected in the way they are today. This statement requires some nuance, as global food markets did exist in the Victorian era. Grain from the American plains was already being shipped to Britain and Europe, and colonial trade routes linked India and Southeast Asia to European networks. But this connectivity was partial and slow. The system was characterized by enough redundancy and regional self-sufficiency that a crop failure in one part of the world did not instantly trigger a price crisis in another. When the Indian monsoon failed in 1876, the primary reason it led to mass death among Indian farmers was not the global market. It was the lack of local food reserves, compounded by colonial policies that actively prevented redistribution. The failure, though its climate cause was global, was devastatingly local in its immediate expression. The global food system of 2026 is a categorically different entity. It is not a collection of regional food systems with trade links between them. It is a single, deeply integrated global machine. It is a system of production, transportation, storage, commodity trading, and distribution that operates in continuous real time across every nation on Earth. Over decades, this system has been optimized for one primary goal: efficiency rather than resilience. Under normal conditions, this optimization has produced extraordinary results in terms of food, production, and distribution, but it also introduces a profound vulnerability. For most of the last half-century, the world has witnessed a remarkable trend, a steady, downward trajectory in the real cost of food. The availability of calories per person has climbed, granting hundreds of millions of people consistent nutrition, a reality that would have been unthinkable under the agricultural productivity of pre-modern times. These are genuine, non-trivial achievements of our modern food system. Yet, this very system, optimized for maximum efficiency, carries a specific structural consequence. The buffers that once provided resilience, the grain reserves, the excess storage capacity, and the general slack in supply chains, have been systematically stripped away. This is the result of modern supply chain management gravitating toward just-in-time models. Under stable conditions, just-in-time delivery, where food moves in near-perfect synchrony with demand instead of being stored at various points, is a model of peak efficiency. But its greatest strength is also its greatest weakness. The model is maximally fragile when faced with disruption, raising a critical question: what happens when the assumption of stability finally breaks down? To explore this, let us walk through what the current forecast configuration could mean for the global food system if it were to come to pass. The scenario is specific enough to be worth tracing in detail. Consider India, the world's largest exporter of rice and a major supplier of wheat. Imagine a significantly failed South Asian monsoon during the summer of 2026. The kind of event that historical precedent suggests would be produced by a coincident strong Pacific, El Niño, and a positive Indian Ocean Dipole. Such a failure would drastically reduce India's agricultural output across a range of staple crops. Based on both historical actions and current policy, India's response would almost certainly include export restrictions, potentially in the form of bans or tariffs on its rice and wheat. This is a familiar playbook. India has taken such measures repeatedly in recent years, including during the price spikes of 2022 and 2023. The announcement of these restrictions would send an immediate shockwave through global commodity markets, as India's role in the global rice trade is so large that its absence creates a genuine supply deficit that other producers simply cannot fill on short notice. Simultaneously, the crisis would be unfolding on other fronts. If this same multi-basin climate configuration also produces below-average rainfall in sub-Saharan Africa and northeastern Brazil, an outcome suggested by historical teleconnection patterns and the Singh et al. Attribution, the world would see a simultaneous reduction in the production of multiple staple crops across several major growing regions. This means that global commodity markets would not be absorbing these shocks sequentially, but all at once. The difference between sequential and simultaneous shocks in a tightly coupled market system is profound and non-linear. Sequential shocks allow the system time to adjust, for buyers to find substitutions, and for reserves to be drawn down. But simultaneous shocks can overwhelm these very mechanisms, because the tools that cushion any single regional crisis are themselves impaired by the other crises happening at the same time. The result would be sharp, rapid, and globally synchronized increases in food prices. This is not a hypothetical model. We have a clear precedent for what this looks like in practice. The commodity price spike of 2010 to 2011 was driven in part by a Russian wheat export ban following a severe heat wave, which occurred alongside simultaneous production shortfalls in Australia and Pakistan. This event demonstrates just how quickly global food prices can escalate when multiple production regions are stressed at once. In that period, global wheat prices roughly doubled over just 6 months. The consequences were not merely economic. That event is cited by analysts as a contributing factor to the social instability that swept across a wide arc of the Middle East and North Africa, creating background conditions that made populations susceptible to the political disruptions of the Arab Spring. And yet, the 2010 to 2011 event was not a full triple basin alignment. It was a coincidence of regional climate stresses, not the globally coherent forcing pattern described in the Singh and Lawal analysis. This historical parallel serves as a stark warning, yet it may only be a pale shadow of what a fully synchronized event could unleash. The dimension of inequality in this scenario is not an incidental detail, it is a core feature. Modern food markets possess a specific property also seen, though through different mechanisms, in the Victorian colonial food system. While the shock is transmitted globally, its effects are not distributed equally. When prices spike, high-income countries have the purchasing power to outcompete lower-income countries for the available food supplies. This echoes the way Victorian British merchants could outbid Indian subsistence farmers for available grain, even amidst famine when colonial markets were open. A global food price spike driven by a synchronized El Niño drought event does not threaten the food security of people in Western Europe or North America in the same way it threatens those in sub-Saharan Africa, South Asia, and parts of the Middle East. These vulnerable populations already spend a much larger share of their income on food, leaving them with less of a buffer in their purchasing power. Furthermore, their governments often have less institutional capacity to absorb the economic shock through subsidies or social safety nets. While the modern system may prevent the kind of mass mortality seen in the Victorian era, it distributes the economic pain of a synchronized climate shock in profoundly uneven ways. And in a chilling historical echo, the populations that would bear the greatest burden today are precisely those that the historical analysis by Singh and his colleagues identified as the most devastated in 1877. The nature of the system has changed, but the geography of vulnerability has not. And this reveals the fundamental truth about our just-in-time global food machine. It is, in fact, a machine. Machines are predictable when operating under the conditions for which they were designed, but they become unpredictable when pushed beyond those parameters. The global food supply chain was engineered for a climate that is no longer fully operative. It has never been stress-tested against a verified triple basin alignment because no one alive has ever seen one. The early signals that such a test might be approaching are already beginning to appear in the data. The danger is that these signals are easily misread as routine anomalies, rather than the first whispers of a larger pattern beginning to assemble. The atmosphere, after all, is not a patient system. When a vast body of water like the Pacific Ocean warms, the effects do not politely wait for it to reach its peak temperature. Instead, the process of reorganizing the global circulation begins almost immediately, rippling outward across the planet. The atmosphere begins to react to the ocean's changing state long before any official thresholds are met. During the early months of 2026, even as the Pacific had yet to formally cross into an El Niño state, the first subtle atmospheric shifts were already being recorded, changes that aligned with an emerging warm event. For instance, climate scientists observed that typhoon activity in the tropical Pacific during this period showed telltale signs of a warming central and eastern Pacific. This included a noticeable eastward migration of storm formation zones compared to their usual climatological positions. Furthermore, these storms were intensifying more rapidly, a direct consequence of the higher sea surface temperatures and greater atmospheric moisture characteristic of a developing El Niño. In the Atlantic, another pattern began to materialize. The very mechanism through which El Niño typically suppresses hurricane formation, an increase in tropical wind shear that destabilizes the structure of cyclones, started appearing in model forecasts for the upcoming season. This type of long-distance influence, or teleconnection, is a well-documented and expected phenomenon. Its appearance in the forecasts suggests that the models see the Pacific's warming as a signal strong enough to project its influence across the globe. These are merely the initial echoes, the first-order atmospheric responses to an oceanic forcing that is still gathering strength. While they are clear to scientific instruments, they are not yet powerful enough to seem unusual to a casual observer. The true importance of these early signals lies not in their individual strength, but in their collective direction. They are all pointing the same way the ocean is pointing. The atmosphere is beginning to mirror a warming signal from the Pacific which, according to subsurface data, is poised to amplify in the coming months. In essence, the atmospheric response is starting to align with what climate models have been projecting for a major El Niño, suggesting the story is beginning to write itself. Part 11. The Silent Amplifiers. Far beneath the turbulent surface of the North Atlantic, a colossal current, a river vaster than any on land, is undergoing a profound change. This is the Atlantic Meridional Overturning Circulation, or AMOC. It functions as a massive circulatory system for the ocean, carrying warm surface waters northward from the tropics. Upon reaching the North Atlantic, this water releases its heat into the atmosphere, becomes cooler and denser, and sinks, eventually returning southward as a deep, cold current. This circulation is the primary engine behind Western Europe's surprisingly mild climate, the reason London's winters are far warmer than its latitude would otherwise dictate. It is a fundamental regulator of how heat is shared between the planet's equator and its poles. Yet, a growing body of research suggests this critical system has been weakening throughout the industrial era. While the exact magnitude and timeline remain subjects of debate and ongoing study, the consistency of this finding across multiple independent methodologies demands serious consideration. The possibility that AMOC may be approaching a state of reduced stability introduces a powerful and unpredictable element into our global climate system. The precise relationship between a weakening AMOC and the dynamics of ENSO is not yet well defined in scientific literature. The mechanisms are considered speculative, and the potential scale of any interaction remains uncertain. There is currently no scientific consensus on how a diminished AMOC would alter the behavior of a powerful El Niño event, or how it might affect the Indian Ocean Dipole or the North Atlantic sea surface temperatures. The third element, in the 1877 alignment, identified by Singh et al. What is clear, however, is that the anomalous warmth observed in the North Atlantic for the past 2 years could itself be linked to these changes in the AMOC. Since the AMOC is a primary driver of heat distribution within the Atlantic basin, any change in its operation would logically alter surface temperature patterns. If the circulation that historically transports heat from one region of the basin to another is now functioning differently, it stands to reason that the resulting sea surface temperature patterns and the atmospheric teleconnections they generate would also be modified. This raises a crucial question. Could the very conditions that mirror the 1877 event be a symptom of a deeper, more modern change in our planet's oceans? This area of inquiry is genuinely at the frontier of climate science, and its uncertainties should not be overstated. However, the possibility that the unfolding El Niño is emerging within a North Atlantic system that is itself in an unusual state is not a fringe idea. It is a legitimate field of scientific investigation. This interaction between two large-scale, anomalous conditions could potentially lead to outcomes that standard ENSO forecast models do not capture, which is another reason to pay closer attention to the current forecast than one might for a typical El Niño. The El Niño forming now is not developing in the same ocean system as the one from the 1990s. It is taking shape in an ocean that is fundamentally warmer in certain basins, with a circulation that may be reorganizing, all within a global climate state that amplifies the thermodynamic reaction to any given forcing. The critical question that models cannot yet fully resolve is whether these background changes will push the outcome toward a more extreme event, or if they will modify it in ways that break the resemblance to historical analogues like 1877. This is a question we must keep in focus as the forecast continues to evolve in the months ahead. Part 12. The Spring Predictability Barrier. In any deep investigation, there is a moment to pause and consider why the narrative we've been constructing might not unfold as expected. For ENSO forecasting, this is that moment. The phenomenon known as the Spring Predictability Barrier is a real and significant challenge that has humbled many confident forecasts in the past. The physical principle behind it is straightforward. The intricate feedback loop between the tropical Pacific Ocean and the atmosphere, where sea surface temperatures influence the winds that, in turn, influence the ocean temperatures, experiences a seasonal low point during the northern hemisphere's spring. This temporary weakening of the ocean-atmosphere coupling makes it notoriously difficult to project conditions with certainty. It is a seasonal fog in the forecast, a period where even strong signals can become ambiguous, reminding us of the inherent complexities in predicting Earth's climate system. The crucial link between the ocean and atmosphere is at its most fragile during a particular time of year. This happens when the tropical solar angle is high. The sea surface temperature gradients that power this connection are at their annual low, and the atmosphere itself is in its most thermodynamically active state. During this period, the slowly developing oceanic signal that climate models are designed to detect can be partially hidden by atmospheric noise that isn't correlated with the ocean's condition. For forecasters, it's like trying to read a message written in a faint pencil script against a chaotic, inky background. Unsurprisingly, predictions made during this spring predictability barrier have historically shown less skill than those made at other times, even when accounting for the forecast lead time. This isn't a critique of the models themselves, but rather an acknowledgement of a seasonal window when the fundamental physics of the climate system make prediction genuinely more difficult. The historical record of enthusiastic spring forecasts is not without its blemishes. A powerful cautionary tale emerged in 2014 when conditions in the Pacific led models to confidently predict a major El Niño. The indicators were all there: significant subsurface heat content, weakening trade winds, and early Kelvin wave activity. Forecast charts from early 2014 looked remarkably similar to what we see in the projections for early 2026. Yet, the anticipated event never fully materialized. The trade winds unexpectedly recovered their strength, and the subsurface heat was redistributed without causing the projected warming at the surface. What ultimately formed was a modest El Niño, a far cry from the super event that many models had foreseen. This 2014 near miss is a story every ENSO forecaster remembers, a constant reminder of nature's capacity to surprise. Both the spring predictability barrier and the 2014 precedent are very real, and they both counsel a degree of humility when assessing the current convergence of forecasts. So, what makes the present situation potentially different from a typical spring barrier scenario? It is the unique combination of factors that have been building. The CFSV2 and NMME models are not merely agreeing on the emergence of an El Niño, they are agreeing on its potential magnitude, which is a much stronger forecasting constraint. Furthermore, the immense subsurface heat content is anchoring these forecasts in ocean physics rather than in more volatile atmospheric changes. This suggests that while the barrier's noise might affect the atmospheric coupling part of the forecast, the powerful oceanic heat engine driving it remains a more stable signal. The IRI's forecast, which places a 70% probability on El Niño during the barrier and rises rapidly after, reflects the judgment of experts who are well aware of the barrier and are already discounting their confidence accordingly. This probabilistic framing is absolutely critical to understanding what is and is not being claimed. When the IRI indicates a 70% El Niño probability, it also implies that in 30% of scenarios, consistent with current data, El Niño either fails to develop or remains too weak to meet the official threshold. Likewise, when the CFSV2 model projects a peak of positive 2.1 degrees Celsius, this represents the central estimate, not a guaranteed outcome. The full spectrum of possibilities extends from neutral conditions all the way to a super El Niño. The uncertainty is real, significant, and should not be understated. However, it is easy to misinterpret what this uncertainty implies. A 30% chance that El Niño fails to develop is not a valid reason to disregard the 70% probability that it will. Similarly, a 30% chance that the multi-basin configuration will not fully emerge is not a reason to stop monitoring its development. The spring predictability barrier means we should approach the forecast with appropriate scientific caution, ready to update our views as new data arrives over the next 2 to 3 months. It cautions us against treating the central estimate as a certainty. What it does not mean, however, is that we should dismiss the signal as mere noise. The barrier reduces our confidence, but it does not invalidate the underlying signal. The most important developments to watch in the coming months will be the evolution of the forecast itself. Will the model's skill increase as the spring predictability barrier recedes? Will the spread of possible outcomes in the ensembles begin to narrow? Will different modeling systems continue to converge on a similar outcome, or will they start to diverge? And crucially, will the atmosphere begin to respond in a way that confirms what the subsurface ocean conditions have been suggesting for months? This evolution will tell us whether we are witnessing a genuine signal clarifying itself over time, or a false alarm that is slowly collapsing under the weight of a reality that refused to match the forecast. Climate models are not crystal balls. They are the mathematical distillation of humanity's best understanding of immensely complex physical systems. While they are truly extraordinary tools, they come with known limitations, documented biases, and a track record of specific failure modes that any honest discussion must address. The CFSV2 model, for instance, has a known tendency to overshoot El Niño peaks in its long-range forecasts. This bias is well documented in scientific literature and operational evaluations. It appears to stem from the model's tendency to overestimate the rate of ocean-atmosphere coupling as an El Niño develops. In the model, the warming ocean drives changes in atmospheric circulation a little too efficiently, which then feeds back into more ocean warming via the Bjerknes feedback. This creates a cycle that can produce an El Niño that grows faster and peaks higher than what the real world typically allows. Knowing this bias exists allows an experienced user to apply a mental downward adjustment to the CFSV2 peak estimate, perhaps on the order of 0.2 to 0.5 degrees Celsius at longer lead times. The NMME, on the other hand, is a collection of different models. This ensemble approach tends to reduce the unique biases of any single model, as those that are overly enthusiastic about El Niño are averaged with those that are less so. The result is a blend that often tracks the real world more reliably than any individual model. But even the NMME ensemble mean has its own skill limitations, particularly at lead times beyond 6 months during the boreal spring. Moreover, the spread of the NMME ensemble, the range of outcomes produced by its constituent models, is wide enough to encompass scenarios from a strong El Niño to neutral conditions. While the mean forecast is positive 2.1, the full range of plausible outcomes spans from positive 0.8 to positive 2.8. The mean represents the most likely single outcome, but the breadth of possibilities the models consider plausible remains vast. Given these limitations, the honest range of forecast scenarios for the coming ENSO season is quite broad. The most probable path forward, according to the central estimates of current models, is the emergence of a strong 2 super El Niño. Forecasters anticipate this event will peak with anomalies between positive 1.5 and positive 2.2 degrees Celsius in the Niño 3.4 region during the Northern Hemisphere's late autumn and early winter. This would mark the first confirmed super El Niño since the major event of 2015 and 2016, but with a critical difference. It would unfold upon a global temperature baseline that is warmer than any previous super event on record. This forecast is not without foundation. It aligns with observations of subsurface ocean heat content and the growing convergence among independent climate models. In my own assessment, based on the available evidence, this particular outcome carries a probability weight of somewhere between 40 and 60%. Though it is important to remember this is an interpretation and not a formal model output. A second, less extreme scenario involves a strong El Niño that remains just below the super threshold. In this case, the peak warming would likely fall within a range of positive 1.2 to positive 1.8 degrees. Such an event would still be highly significant, comparable in strength to the El Niños of 1998 to 1999 or 2009 to 2010. However, it would likely not reach the intensity needed to trigger the multi-basin alignment risk that has been a focus of our concern. Under this possibility, the triple forcing pattern would be considerably weaker, as the Pacific Ocean's contribution would be less intense. This alternative outcome gains some credibility from adjustments made for the CFSV2 model's known downward bias, and from the historical frequency of forecast errors across the spring predictability barrier. I would assign this scenario a probability of roughly 25 to 30%. The third potential outcome is one in which the El Niño development either fails or is significantly weakened, analogous to what occurred in 2014. In this case, the warming might barely cross the El Niño threshold, or not cross it at all. For this to happen, the Pacific trade winds would need to recover their strength, and the crucial coupling between the ocean and atmosphere would have to stay suppressed through the critical spring barrier window. This is the future where the 2014 analog proves most prescient. Given the immense depth of the current subsurface heat anomaly compared to 2014, this scenario seems less probable than it might in other years. Still, its likelihood is not negligible, perhaps sitting at 15 to 20%. Over the next 2 to 3 months, we will look to key observational tests to distinguish which of these futures is unfolding. The evolution of the trade winds in the central and western Pacific, the rate of sea surface temperature warming in the Nino 3.4 region, and the behavior of the subsurface heat content as the Kelvin waves arrive in the east. These real-world indicators, more than any model, will tell us which story we are living in. Before we proceed to the final act of this narrative, it feels necessary to take a deliberate pause. We have arrived at a point where complex scientific discussions, especially online, can become fertile ground for misunderstanding and misinformation. If you have spent time in the corners of social media where climate discourse intersects with conspiracy theories, you likely know what is to come. So, to ensure we can have an honest conversation about what this story truly represents, it is essential to first clarify what it is not. Clearing away these misconceptions is not merely a courtesy. It is a prerequisite for understanding the genuine scientific developments at play. Let's begin with the subject of geoengineering, as it will inevitably surface if not addressed directly. The claim typically suggests that the anomalous warming we are observing across the Pacific, Indian, and North Atlantic Oceans is not a natural phenomenon. Instead, it is presented as the result of a deliberate atmospheric intervention, perhaps chemical spraying or aerosol injection, some form of classified technology used by powerful institutions to manipulate the global climate. It is important to engage with this idea seriously, because those asking these questions have often correctly noticed that something unusual is happening in the climate data. That instinct is not wrong. The anomalies are real. However, the geoengineering explanation fails on the most fundamental physical grounds, and the numbers involved are not even close. The Pacific warm pool, that vast reservoir of thermal energy in the western equatorial Pacific, now moving eastward, contains more heat than our entire civilization has released by burning fossil fuels throughout the whole of the industrial period. This is not an exaggeration. The total thermal output from the first coal-powered steam engine to every vehicle on the road today is dwarfed by the energy stored in this single oceanic feature. Any technology capable of modifying that reservoir on a scale large enough to generate a super El Niño would need to operate at a power level that would itself be the most significant energy event in human history. It would be visible, measurable, and impossible to conceal from the global network of ocean sensors, atmospheric stations, and independent scientific institutions that span dozens of nations with competing interests. Furthermore, the stratospheric aerosol injection schemes that are seriously studied by researchers are specifically designed to reflect a small fraction of incoming solar radiation, thereby producing a cooling effect. They are not designed to heat the ocean, nor do they. Any imagined classified version of such technology would still be bound by the laws of physics and the immense energy scales required. If you have encountered content claiming otherwise, you have encountered science fiction dressed in the costume of technical language. The costume may appear convincing from a distance, but it does not hold up to scrutiny when you check the numbers. Now, let's turn to the sun, a topic that is scientifically more nuanced and, as someone who covers solar activity here on Calm Space, a genuinely fascinating area of geophysics. The current solar cycle 25, is tracking toward a moderately active maximum. It is running slightly above the initial predictions. a development that is certainly notable and worthy of its own discussion. Yet, it is crucial to distinguish between slightly above average and anomalously extreme. The total effect of a solar cycle of this magnitude on global temperatures is on the order of 0.1 degrees Celsius, spread across the full 1-year cycle. While this is a real and measurable signal that is important for precise climate attribution, it is 1 to 2 orders of magnitude smaller than the powerful El Niño anomalies we are examining in this story. The sun's influence is a real piece of the climate puzzle, but it is not the primary driver of the events currently unfolding in our oceans. A warming of 2 degrees Celsius in the Nino 3.4 index simply does not find its explanation in the solar cycle. The sun's influence lacks the necessary force, is not concentrated in the correct ocean basins, and fails to generate the specific pattern of subsurface heat accumulation in the Western Pacific that is actively being observed by the Tau mooring array and the Argo float network. This raises an important point about scientific inquiry. While the connection between solar activity and ENSO variability remains a legitimate area of research, with peer-reviewed papers exploring potential stratospheric pathways, these studies are exploratory and the effects they have found are small. There is no credible, peer-reviewed evidence to suggest that solar activity is the primary driver of the current forecast. At Calm Space, our guiding principle is to follow the evidence, even when the sun is not the answer. This brings us to a second point, the claim of data suppression. There is a persistent idea that NOAA might be hiding the true forecast, manipulating its models, or that the very information described here is being kept from public view by institutional gatekeepers. Let us be unequivocally direct. The data is public, all of it. The CFSV2 forecast output is available on NOAA's website, updated daily and downloadable by anyone with an internet connection. The NME ensemble is public, as are the IRI forecast plumes. The Argo float data, which provides real-time subsurface ocean temperature measurements from a global network of autonomous floats, is also entirely public. So too is the data from the Tau and Triton mooring arrays, the fixed sensors measuring conditions along the equatorial Pacific. The analysis in this video does not come from leaked documents or insider sources. It is built entirely from publicly accessible databases that anyone can query today for free. If the data is so open, why is the story of a multi-basin compound event not more prominent in mainstream climate coverage? The answer is not that someone is suppressing it. The reality is considerably more mundane, and in some ways, more frustrating. The significance of this particular signal can only be found by synthesizing observations across 3 separate ocean basins, understanding the complex teleconnection mechanisms between them, and linking that synthesis to a historical attribution study that most climate journalists have never read. This kind of deep dive does not fit neatly into the standard format of an El Niño forecast story. A standard El Niño report follows a clear narrative structure. The Pacific Ocean warms, certain regions experience drought, others face flooding, and here is what it means for hurricane season. That story is simple, familiar, and can be told in 400 words. The multi-basin compound event story, by contrast, requires explaining what the Indian Ocean Dipole is, why the North Atlantic matters, what teleconnection stacking means, and why the coincidence of all 3 basins is more critical than the magnitude of any one. That story takes considerably longer to tell. The media environment in which climate journalism operates does not consistently reward longer or more technically complex narratives. It is a crucial distinction to make. Complexity is not conspiracy. It is just complexity. The uncomfortable truth, then, is that the absence of mainstream coverage of this particular configuration is not evidence of suppression. It is evidence of a communication gap, a divide between what the peer-reviewed science has firmly established and what the science communication infrastructure is currently translating into public discourse. And that gap, not any conspiracy, manipulation, or classified weather technology, is the actual problem. This is because the configuration that the 2018 paper describes is assembling in real-time observational data. Right now, it is detectable, nameable, and discussable using publicly available information. We are in the window where this information is most actionable, the period before the event fully verifies, when preparation and awareness still hold their greatest value. The data is raising a question, not a hidden question, not a suppressed one, but a question sitting in a peer-reviewed journal written by scientists who did the hard work of attribution. They described the mechanism behind the worst climate catastrophe in the modern record. And now we are seeing that pattern match in real time against ocean observations that anyone with a browser can verify. That is not a conspiracy, it is a finding. The only reason it feels like a secret is that not enough people have been saying it out loud. Now, we need to sit with what happens if the finding is right. Suppose the forecast verifies. Let us imagine that over the next 2 months, the spring predictability barrier recedes, the ensemble spread narrows, the trade winds weaken, and the oceanic Kelvin waves complete their eastward transit. In this scenario, the Nino 3.4 index would cross positive 2 degrees Celsius by October and continue climbing toward positive 2.2 degrees Celsius by December. Suppose, too, that the Indian Ocean Dipole commits to a positive phase in September and October, precisely when the El Niño is approaching its peak. And suppose the North Atlantic remains anomalously warm, as it has for 2 years, allowing atmospheric teleconnections from that warmth to compound the circulation anomalies that the Pacific and Indian Ocean are already driving independently. If this happens, the multi-basin alignment that Singh and his colleagues described in the 1876 to 1878 record would assemble itself in the global ocean in the second half of 2026. What would that world look like? The physical impacts would be real, measurable, and significant. Global mean temperature would spike. The 2026 annual mean global temperature would almost certainly set a new record, potentially by a substantial margin. This is because super El Niño events add roughly 0.2 to 0.4 degrees Celsius to the global mean temperature in the year of their peak and the year that follows, all on top of an already record warm baseline. Since the 2023 and 2024 global temperature records have already been broken sequentially, a super El Niño peak in 2026 would almost certainly extend that sequence. It would also push global temperatures further above the 1.5 degrees Celsius Paris Agreement threshold, a line the international climate community has identified as a target for limiting the worst-case impacts. Regional drought and rainfall patterns would also reorganize dramatically. The historical Teleconnection record for strong El Niño events is fairly consistent, giving us a glimpse of what to expect. This includes reduced rainfall across South Asia during the monsoon season and decreased precipitation across both sub-Saharan Africa and northeastern Brazil. The consequences of a powerful El Niño would manifest in dramatic shifts to global weather patterns. Regions like Australia and parts of Southeast Asia could experience diminished rainfall, while across the eastern tropical Pacific, areas of East Africa, and the southern United States, precipitation would likely be enhanced. We must consider these potential anomalies in the context of a world already fundamentally changed. Today's atmosphere holds roughly 7% more moisture than it did in the pre-industrial era, a fact which suggests that any climatic shifts would be amplified. This could mean that droughts become even more parching and floods more devastating, pushing the extremes further from their historical norms. The strain on the global food system would not appear all at once. Instead, it would likely unfold over several months, beginning to materialize in agricultural outcomes even before the El Niño event reaches its maximum intensity. For instance, if the Indian Ocean Dipole is already in a positive phase and the Pacific continues its warming trend, anomalies in South Asia's monsoon rainfall could become apparent between June and September of 2026, with measurable impacts on crop conditions by July. Later in the year, from October through December, circulation changes tied to El Niño typically affect rainfall in sub-Saharan Africa. This staggered timeline of compounding agricultural stress, should the alignment occur, could unfold over a period of 6 to 12 months. This provides a potential, if challenging, window for commodity markets, food policy institutions, and international aid organizations to anticipate and prepare for the scale of the shock they might face. The ripple effects would extend far beyond agriculture, touching nearly every facet of modern life. Heat waves across Asia could drive up energy demand, while infrastructure in the enhanced rainfall zones would be stressed by extreme precipitation. Public health systems would also face immense pressure, particularly from heat waves in the densely populated urban centers of South and Southeast Asia. The combination of spikes in commodity prices and reduced productivity in climate-sensitive sectors would trigger significant economic disruptions. However, the burden of these impacts would not be distributed equally. The world's poorest countries, especially those in sub-Saharan Africa and South Asia, where climate sensitivity is highest and the capacity to adapt is lowest, would find themselves disproportionately affected. In wealthier nations, the consequences would still be significant, but they would manifest primarily as economic challenges rather than direct physical threats to survival. It is crucial to state clearly that this scenario does not imply a direct repetition of the catastrophic events of 1877. To invoke the memory of an event that led to an estimated 50 million deaths requires an honest assessment of what has and has not changed. The immense mortality of the 19th century famine was the product of a specific intersection, a powerful climate event colliding with a unique set of governance failures. These included colonial extraction, rigid ideological opposition to market intervention, and the complete absence of any international humanitarian infrastructure. These specific modes of failure are not the dominant risks we face in a potential 2026 event. Today, an international humanitarian system, for all its imperfections, does exist. National food security programs, however inequitable, are in place. Furthermore, early warning systems that were unimaginable in 1877 can now detect monsoon deficits and issue food security alerts weeks in advance. The direct, widespread famine that Victorian colonial administrations permitted is not the primary danger today. But this does not mean our modern system is immune to the stress that a verified triple basin alignment would create. Our contemporary global system has its own distinct vulnerabilities, which are different from those of the Victorian era, but by no means smaller. We must ask ourselves what these new fragilities look like. Consider a globally synchronized food price spike occurring within a commodity market that operates in real time. This system grants immediate access to high-income buyers while simultaneously locking out low-income buyers, transmitting a shock from a production region to a consumption region in a matter of hours, not weeks. This represents a fundamentally different kind of vulnerability than colonial extraction, but it is a profound vulnerability nonetheless. Political systems already grappling with inequality, polarization, and post-pandemic stress would be forced to absorb these food price shocks on top of their existing fragilities. The geopolitical stability of regions already contending with water insecurity and agricultural challenges, such as the Sahel, the Horn of Africa, the Indian subcontinent, and the Middle East, would be tested even further. These are not speculative scenarios drawn from science fiction. They are possibilities grounded in recent historical precedent, such as the food price spike of 2010, 2011, and the commodity disruptions that followed the 2022 war in Ukraine. Therefore, the realistic impact of a super El Niño with a triple basin alignment in 2026 is not 50 million deaths. Instead, it is a global economic shock of a massive scale, one that would be disproportionately absorbed by the world's most vulnerable populations. Such an event would occur at a moment when the institutional and political systems designed to manage these shocks are already under considerable strain. While this outcome might not produce mortality on a Victorian scale, it would represent a genuine and significant stress test of the modern world's ability to handle synchronized global climate disruption, a test of a magnitude our interconnected system has never before faced, and for which our preparations are both uneven and incomplete. Let us return to where our journey began, the present moment. The Oceanic Niño Index, a key metric, currently sits at a quiet plus 0.16 degrees. On the surface, the ocean appears calm, yet the CFSV2 climate model is projecting a peak warming of plus 2.1 to plus 2.2 degrees Celsius, a forecast supported by the NMME model suite. The International Research Institute for Climate and Society shows a 70% and rising probability of El Niño developing during a period historically known for its low forecast skill. Beneath the surface, a pool of warm water in the western Pacific, measuring 29 to 30 degrees Celsius, is moving eastward in the form of Kelvin waves that will not be detectable at the surface for months. Meanwhile, the Indian Ocean is trending toward a positive IOD, and the North Atlantic is anomalously warm for the second year in a row. A peer-reviewed paper, published in the Journal of Climate in 2018, noted that the last time all three of these ocean basins aligned in this specific configuration, somewhere between 30 and 50 million people perished. It is essential to state this plainly. None of this means that history is repeating itself. The current data is not a prediction of famine, and no credible scientist is making such a claim. The models contain significant uncertainty, and the spring predictability barrier limits our forecasting ability at this time of year. The 2014 analog, where a similar forecast did not fully materialize, reminds us that multiple plausible scenarios exist. The forecast could fail to verify at a super El Niño magnitude. The Indian Ocean Dipole might not lock into a positive phase, or the Atlantic's connection to the Pacific and Indian Ocean forcing could be weaker than the 1,877 record suggests. These are all genuine and non-trivial possibilities. What the data shows is something more specific than a prediction of catastrophe, and in some ways, more significant. It reveals the early assembly of the precise configuration that climate science has identified as the underlying mechanism for the most lethal climate event in modern history. We are not looking at a prophecy of doom. Rather, we are observing the pieces of a known, powerful, and dangerous natural pattern beginning to fall into place. The question is not whether the past will repeat, but how our modern world will respond to the echoes of a pattern it has not faced in over a century. The configuration is now visible in real time, appearing in publicly available data, while our most advanced forecasting systems, from independent starting points, converge on the same potential outcome. The question our models are built to answer is whether this alignment will materialize, and we will certainly know more in 2 months than we do today. But the truly unanswerable question, the one no model can compute, is what happens to our modern world if it does. This is because our global civilization, with its intricate supply chains, commodity markets, food security architecture, and political institutions, was never constructed to withstand a stress test of this particular nature. The possibility of a verified triple basin alignment was simply not a design parameter. The engineers of our global food networks, the architects of international humanitarian aid, the designers of commodity trading, and the authors of national food security policies were all working without this critical information. For most, the Singleton analysis was not on their desks as they built our world, and for many, it still isn't. The catastrophe of 1877 was not, however, an unavoidable event written solely in the physics of the climate. The 50 million lives lost were not a direct result of the drought that caused monsoons to fail across 2 continents. They perished because the climate created a profound stress, and the human systems of that era buckled under the pressure in ways unique to the institutions, ideologies, and power structures of the Victorian age. This historical precedent offers a sobering lesson. The drought provided the pressure, but it was the design of human systems that ultimately determined the outcome. If this configuration does indeed verify, the 2026 version of that question will not be about Victorian colonial policy. Instead, it will be about our own modern systems, just-in-time supply chains, the dynamics of commodity markets, the threat of export restrictions, food price volatility, the capacity of humanitarian funding, and the political will of governments to prioritize global response when facing their own domestic pressures. Our contemporary system is, in most respects, genuinely more capable than its Victorian predecessor. But this raises a crucial question. Is it capable enough in the specific ways a synchronized, global agricultural shock would test it? The honest answer is that we do not know. We have never conducted this experiment. The modern global food system has never been subjected to the full, synchronized stress of a verified triple basin alignment at super El Niño magnitude. We have only partial analogues, like the price spike of 2010 to 2011 or the disruptions of 2022, but none possess the full scale and synchronization that the Sing-Al configuration implies. Over the next 60 to 90 days, the forecast will sharpen as the spring predictability barrier falls away. The ensemble of predictions will narrow, and the physical evidence will begin to mount. We will watch the trade winds to see if they are weakening or recovering. We will watch the Indian Ocean to see if the IOD is committing to a particular state. And we will watch the North Atlantic to see if its warmth is coupling to the global circulation as the historical record suggests it can. This period is a critical window of observation, where uncertainty will steadily give way to clarity. The signal will either intensify into a clear and present danger, demanding the attention of every institution involved in food security and economic stability, or it will soften into a strong but more manageable event with significant yet localized impacts. Herein lies the paradox of preparedness. The systems that would need to respond to a verified triple basin alignment, the agricultural commodity reserves, the international food monitoring networks, the prepositioning of humanitarian aid, and the policy frameworks for coordinating export restrictions all operate on lead times far longer than 60 to 90 days. The lag between detecting a clear climate signal and mounting an effective systemic response is measured not in weeks, but in seasons. This means the window for preparation is not when we have certainty. The window for preparation is now. It is now because the cost of preparing for an event that doesn't fully materialize is minor compared to the devastating cost of failing to prepare for one that does. The models are not predicting a famine. They are predicting a test. They are telling us that the ocean is loading, the basins are shifting, and the configuration is assembling. Sometime in the next 6 months, we will discover whether the physics cooperates, the atmosphere couples, and the Indian Ocean commits, bringing the triple alignment into full existence. If that happens, the only question that will matter is not whether we could have seen it coming. The data clearly shows that we could have. The question will be whether we were watching carefully enough to act while there was still time to make a difference. It is a test not just of our systems, but of our foresight, a test of whether the institutions we built to manage planetary scale stress were designed to respond to a signal that is forming right now, visible in public data, described in peer-reviewed science, and pointing toward a threshold humanity has crossed only once before and would desperately wish never to cross again. The ocean surface is quiet for now, but deep below, the subsurface has already made its decision. The defining question of our near future is what happens when that decision reaches the surface, not just in the Pacific, but across all three basins at once, in a world that has never been tested by what they can do together. The spring of 2026 is just beginning to ask this question, and we are going to find out the answer, whether we are ready for it or not. The only thing we do not know yet is which parts of our world will be the first to fail.